Hello, Dr. Farag. This is Josh Jaslow. I am doing a re-recording of my final video because I came to my attention that I forgot a few things to discuss, so I figured I would just do it all over again, perhaps be a bit more eloquent this time. So anyway, I'm going to walk through first a run through of actually running the program, and then I'll talk about how my code works after that. So first, as per my README, you need Docker Desktop, like I have. Make sure that's running. Make sure you pull the image from Docker Hub. Then make sure you have Xcorts installed. These are instructions for Mac since I have a Mac, so make sure you have Xcorts installed. Then enter the following commands to make sure that it properly connects to Docker, and then I can show my program on the screen. So first, I already have these preloaded because for some reason I can't copy and paste into the Xterm terminal. So first you have to set the IP variable here. This just makes it easy so you don't have to copy this entire thing into the final command. Then next, we have to run xhost plus IP. I believe this lets the Xcorts connect up to the same thing with Docker here. Then finally, the Docker run command. Hit that, and my name search engine opens up. So first, I'm going to run this twice. I'm going to choose first just a few files, and then I'll run it later with all the files just to show that it works in several instances. So just going to run with all the King Henry files first. Construct indices. So I did say I'll go into my code later. One thing I will point out while we're waiting here, because this will take some time to construct the indices, is I don't actually send up any files. I simply send up an argument that has all of these files kind of joined together, and then my inverted indices program on Google Cloud can just filter out the files that are whitelisted here that I've chosen. So that saves me having to figure out how to actually upload files as per your instructions. We don't have to do that. Alright, this should be coming to a close. It takes about 30 seconds to run, so it should be there soon. Come on. Oh, you know what? I realized, okay, well, it just finished. I just realized that no, the 30 seconds I was thinking of is the time it takes to perform the search return operation, which is the one that actually I need the one that I actually implement the timing for. Yeah, this one actually takes about a minute and a half or so. So next, let's do a search for term. So I'm going to search for the word king. I would assume that in King Henry files it would show up quite a bit. So this one will in fact take about 30 seconds to run. I'll just hold on until then. There we go. So now it is finished. Executed in 31.8 seconds. So pretty close. I know this varies sometimes. So it can take around anywhere from 30 to 40 seconds depending on the query. So here I have my doc IDs, doc folders, doc name, frequencies. the doc ID I made with using a hash function, so that it'll make every file name will create a unique doc ID, but the same file name will always generate the same doc ID in theory. Do the hash function, and there'd be a highly unlikely chance for collisions or anything. So these should all be unique. As you noted before, I would just keep these all in the flat folder on GCP, so that's why they all say input here. The doc name, and these are all ordered by their frequencies. So I wanted to do a little experiment to show you that this actually works, or at least it's self-consistent. So, well, that's some weird visual bugs there. So if I add up all of these frequencies, let's do 394 plus 239 plus 126 plus 130 plus 128, get 1027. Now, if the indices are self-consistent, then king should show up as 1027 in the top n, which is what I'm going to do. So just to be sure that we'll get king in there, because I'm sure there's a lot of repeated words. I'm going to do top 30. So this will take a bit of time as well, but roughly equal to the same amount of time it takes to do the word search. There we go. All right, so now I have the top 30 words from all of the King Henry files. As you can see, king is here, and then 1, 2, 3, 4, 5, 6, 7, 8th spot, 1027. So shows that, I'm fairly certain this is the correct answer, and it shows it is also internally consistent with the word search and reporting those individual frequencies within each file. As you can probably tell, I have used a stop words list, and I'll go over what words I used when I go over my code a little bit later. First, I'm going to show you just to show that it works. I'm going to run the whole thing again. I just had to reload it so I get back to the choose files here. And I'm going to choose all of them here. Struct indices. So I'll mention this on my README as well, but the choose files, I have, just a list of a flat list of the files as well in the Docker file system here. I'm not quite sure why. I don't really know enough about Xterm and Docker to know why it starts me on the root folder. I wasn't sure how to move my files folder inside that one, but if you just go back up one to the topmost folder, the slash, and the data folder should be right there, and you should be able to find the files. I feel like I should have the Jeopardy theme music kind of in the background here while I'm waiting for this. Probably the most annoying part about writing or connecting the GUI with the cloud program or the cloud jars is just waiting for it to return. It's like ended up eating out a lot of my time. All right, so I'm just gonna do top N. Just do the top 50. Just to show you what it would look like with all of the files loaded up. Again, Jeopardy music would be nice here. Aha. There we go. So these are the top 50 words without the stop words. The top 50 words from all of the text files that he provided. So it looks like he is right there with 35,000. Wow. So yeah, that was kind of a run through of the program itself. And as I have noted in my README, I'll be keeping my cluster running the entire week, basically until you're finished grading, or until you get back to me that you're finished grading. So you can use my cluster to run all of these, since it has my jars and everything on there. All right, so I might keep this up for reference for the code, but let's dive into the code. So one thing I'm actually really proud of that I designed here was I used the MVVM pattern, which stands for Model View Model. I didn't quite use the entire pattern. I didn't really use much of a model in the sense, but I still have the view and the view model created, and I really like this because like I drew on my iOS experience when creating this, and it makes everything a lot cleaner than I would have otherwise done, just throwing everything together. So this is my runner class, but it's also my view model. So I just instantiate itself basically in the main method. And so the way I handle things is I have one window, or I guess one frame, and then all of my other panels just get swapped out, and then it repaints and it will show a new screen. And that's how I'm able to swap through all of them. So as a view model, this class will handle all of the logic, all of the coordination between everything, so that my views only have to worry about, taking input and presenting things to the user. And they don't have to worry about any of this logic. So run frame basically just runs everything. I collapsed everything. I didn't realize that it would collapse the entirety of of everything. I thought it would just collapse the topmost one. So I might have to expand some of these. All right, let me just let's just expand all. Okay, that'll be easier. So run frame basically just constructs everything and then starts the first panel, which is the load engine panel. And construct frame just creates the frame for me. Construct all panels just initializes all of the panels and sets them to the variables. And then these are just the helper functions to do that. So it's a bit cleaner. Now I have the delegation functions here. So basically, let's go, for instance, to the search term results panel. So this is my view. All I care about in this file is the view code and the code to directly interact with the view itself. So I have all of my view code basically written here in the initialize function. A lot of this was created by the window builder, although I have modified it after the fact. And then I have my delegate functions calling back to my view model. So go back will actually just tell the view model to go back, and that'll change the page since it knows about all the pages, and this view only knows about itself. And this also returns itself just so I can get actually the panel this is built on. So it's just a regular class. It implements my panel interface, which just provides a few functions that I wanted all of them to have. That was just for cleanliness, but it itself is just a regular class. I didn't actually extend the JPanel class because I wasn't confident that I would be able to make that work, since I haven't used the Java Swing and those GUI libraries too much. So anyway, I have the panel here, initializes itself, It sets the view model, which is very important. So both this has a reference to the view model has a reference to this, and then they can talk to each other. And all of the views can all talk to the view model can talk to all the views, and it's nice coupling there. Construct table data just replaces my dummy data here. This is just the data from the mock-up PDF. This actually replaces all of the data in the table with the data that I get from my word search result array. This is just a custom class here, and then it will just make sure the table has the model and it just tell it to refresh itself basically. I think that's it. I'll go into my class here really quick. So at first I just parsed the data out in like strings, and I had arrays for each variable here. But then I realized that I wouldn't be able to coordinate the sorting of each array perfectly, because I can sort the frequency array by frequency, but then how would that sort the other arrays according to the frequency array sorting? So I realized then that just creating a class to hold all of my result data in one object made it a lot easier, because then all of these are linked together, and so if I sort by frequency, which is what I do here, then these will get pulled along with it. And so in the search results, then they would all be so it would make sure that this frequency is still matched up with this, still match up with this, still match up with this, without getting these all mixed up, getting the individual kind of columns out of order. So that was my search term results panel. Most of the views are very similar. They're just the panel code, the view model code. So I won't go into those too much. I might just go scroll through really quick, but they're all very, very similar. So yeah, I'll open those up really quick, but I'm not going to spend too much time talking about them. See here. So I have the top end results panel as well. So this is very similar because there's just another table here. I just have fewer columns, but I have very similar stuff because I use the same function. The initialization is very similar. They're very similar. The GUI elements in here, same go back, same get panel. What else? Let's see. I have the load engine panel. So this again is very similar. It has a lot of code to just write the view out, and I had to make sure I embedded the scroll pane in a separate sort of layout. I still don't quite understand the layouts perfectly, but after doing some researching online, that actually embedding this in its own Spring layout, embedding the files list within the scroll pane is better, because then you can actually scroll the files list and it'll take care of that instead of trying to expand the size of the window to fit the files list. That makes sense. Yeah, very similar. Just some more. These are some private functions. I'll just call the view model here. The view model calls these to set the text here for the file list. Very, very straightforward. Let's see, end value panel is, I believe that's where I select the end value. So enter your end value, type your end, search box. Pretty straightforward. Calls the view model function here to kick things off. So yeah, these are all very similar. Yeah. So let me get back to the runner. So when I click the button, so this is handle choose files, and that will then jump to the Oh, so that'll fill those in. And then when I click inverted indices from there, handle constructed indices gets called. I have a list of files that I replaced the forwards, like the new line character with the comma, just because I wasn't sure how command line arguments would deal with having new line characters. Like normally, if I try and add, if I try and give it an array separated by, or a string separated by new line characters, when I'm typing something in command line, if I hit enter, it'll actually, it'll just run the command instead of actually, having a string. So that's why I just replaced them with a comma just to be safe here. I use random here because that way I don't have to worry about deleting any of the output directories. I can just, eventually we'll get to the point where it'll like collide with something else, but it hasn't happened yet. And just to give it a big enough number, hopefully it shouldn't happen in the near future. But if there is any doubt, you can just go into the HDFS cluster itself and delete all the output folders. It should be good. I guess thinking about it, maybe doing something like the current system time millis, something that only counts upward would be better, but oh well, this works. Let's see. So basically, I create my input and output directory strings and add those to my arguments list. Then I only need to. I don't actually need to initialize the cluster. I don't need to start the cluster on Google, so I don't have to use that code. I only have to instantiate it once, or initialize. I get those two words confused: initialize and instantiate. But I only need to instantiate these objects once because they never change. The data proc will always be there. The credentials will always be there. So I just set my local or like my global variables up there to these, and I can just call them later. That just creates the or gets my credentials from my credentials file, and it initializes my data proc object in my runner here, so I can interact with it. Then everything with executing a job, I've actually refactored into its own function. So this is the name of the main class. This is the name of the jar, and these are the arguments. Let's jump down there. Main class jar argument list. So this basically runs through a bunch of things to create the job and then submit it, execute. Then I want to know, as you saw on Xcourts here, I actually have my status here. So I want to repeatedly know, where is it, how are we doing. So basically every half a second, just ping it. Sometimes it gets held up a little bit, but for the most part, it keeps me well informed while I'm waiting. And then once that's finished, it'll print that out, and only if it returns done will it actually return true here for this entire function. Because I only wanted to move on if I'm done. That's one thing that helped me figure out when I was having issues, is if I wasn't looking at the command line, I could at least tell, okay, well, it returned, but it didn't actually go anywhere, therefore I had a problem. And let's see here. So otherwise return false, and I private print the stack trace, so that's been very handy. Yeah, so that returns. So we just finished here, and then I don't actually have to worry about getting anything from the cloud. As long as I know it's successful, I can just change view to my Indices constructed panel, and that's where I can choose my which operation I want to do. So then I go into that view, have the two buttons, and when I select search return, for instance, a lot of the same things happen. I create my input and output directories, my args list here. I have a separate random thing here because I don't want it to. I want to be able to. If I have the same random number, if I never reset this and just make it a variable or something, then I'll only ever be able to run this once. And if I, for example, I go back and I want to search for term again, it'll use it, if it uses the same random number instead of regenerating it. Excuse me. Then I would run into a collision because the output directory already exists. So I just make sure I create a new one every time, and that goes in the input and output directory. So I know I can always have a new. I can both find the one I created. The output directory has the random. Sorry, the inverted random is just the random number from the inverted indices. So I can just get the output directory of inverted indices, use that as the input for this function. Then create the args list. I have my start and end time here, just because I found this easier than using the start or doing a timer on the actual job on the cluster. I found it easier just to return, just to get the time as soon as it returns back. So essentially the same. So it does another execute job here, which time with the word search. And if it's false, it just returns. So I don't actually go anywhere. It'll just stay on the search, enter your word screen. Otherwise, it'll continue. And now here is where I collect my results from Google Storage. So I use the buckets, and here, just as another try catch, gets to storage, opens up the page with the blobs, gets all the blobs. Basically, it creates a string out of them, and nice thing is it only makes one string, so I never have to worry about having a whole array or anything. So the string is everything kind of stitched together, and so that is actually what happens next. Is I as long as it's not empty, I split it out in tokens using tabs. Using the tab, and then I can get the word occurrences. So then I have, I'll go over this later in my word search jar or word search program overview. But then I get I split them by the comma, and then from there I can go through each one and add a new word search result to the array, and then from there I can export that to the search term results panel and then change the view. And then there's these two things: just change the word, change the time, and that's that. And then it's very similar for top end: input and output directory, args list, execute job, collect results. Same thing, checking if it's empty. The results are a bit simpler with the top end. There's only two things I need from each, so it's a bit shorter here. And once I parse out the string into a whole array, or array list, I guess I should say, construct table data, update the number that I had, and change the view. And that's about it. Goes back to wherever. Always goes back to the indices constructed panel, so I don't have to worry about passing anything there. And then change view just changes to whatever one I want to. So, nice. Another nice thing about using an interface, I can actually just say I want to change view to any panel that implements this, and I don't actually have to worry about doing one for each different panel. I can just make sure I can just use the interface here. It cleans things up quite a bit. I get panel function I did before, repaint, revalidate, and I believe that's it for here. I have this is job finished. That just that's for here. So that just takes all of this and refactors that so it's not kind of in the middle of this while loop here. And that's about it. So next I'm going to open up my 3 jars that are on Google Cloud and just run through those briefly. I know you know about MapReduce, and I know you're aware of how much I know about MapReduce, so I'm just going to gloss over them, just show you kind of my implementation, but I'm not going to explain them because we both know how they work. So first with the inverted index, mapper reducer. So my mapper class, do a few things here, since this is the one that requires the most setup, I guess, is first I have my files list for my configuration. Excuse me. So this is the files list that I pass in, and this basically just creates an array of files, and so then I can check those later to see if the current file is in there. So next I actually get the current file of whatever I'm looking at, split it out into file name and file folders, and then just aggregate that into a string so I can add that into the context later. Current files, file name, so that actually enables me to check my current file against my whitelist of files here. And these are all my stop words. So these are basically just the 10 most common words in the English language. Just do a quick Google search, pick the top 10, and there we go. And if you notice here, these are all lowercase. I actually did make everything lowercase as I'm ingesting it into the map function here, just to make everything kind of level playing field, so I don't have any duplicates, or capital King, lowercase king. I don't have to worry about that. And that enables me also to make these kind of case agnostic, if you will. So the map function is very simple. As long as the file's whitelist does not contain the current file, as long as it does contain the current file, we're fine. If it doesn't, we'll just return and we're done mapping. String tokenizer here, this tokenizes everything, but I use a bunch more delimiters than the standard. The standard delimiters are just these 4: space, tab, new line, or carriage return. And these 5. The function the carriage feed. I don't quite know what the /f is. I also added the quotation mark. I just had to give it an escape character, otherwise it would treat it as part of the string here. And then a bunch of the other standard character from punctuation, so that none of those would get ingested in. And yeah, so then that's the kind of the primary, or I guess the first stage of filtering out. And then my second stage actually here is the stop words. I don't want to include these here because they'll get confusing with all the characters. So I've just added the after here, making sure that the stop word list does not contain the current word. If it doesn't, we write the context with the file name and path, and that's mapper. Reducer, very simple. I just have a hash map. Didn't need tree map or anything like we've been doing in some other homeworks. Just have a hash map. And the nice thing is, since I can map since there certainly could be duplicate words, it'll just add 1 for each of those, keep them in the hash map, so then I have a very accurate count of which of all the words and their files and the counts and everything. And I actually then append on to the word part of it. So here I actually then have an index. So I'm at a loss for words. Basically here, I want to create kind of the final version. So I have my file name and file path, I believe is right here. File name and file path, because that's the string here. Then count is the value, and then comma, and then once those get written to, those will end up all together in a single line. So basically, every new file that word occurs in, it has the count for that file and also the file name, and they're all separated by commas. And then once that entire word, the word and all of its information is done, gets written to context, the word, and then the indices, that string here. Yes. So that's the reducer. Let me just go over the driver really quick. But kind of basically a bog standard driver. Here's where I get in my files list from the last argument. Nothing really special happening here. So let's move on. All right. What's next? Top end using inverted indices. All right. So mapper. Very straightforward. It just takes in basically all of these. All that's doing right here is just breaking apart kind of the structure I made in the inverted indices just to extract the count from there, and then basically write the word and the count, and send those along to the mapper, or sorry, to the reducer. Oh my, this recording is getting long. Top end reducer. So now that I'm here, I just set up a tree map, so it's very similar to our least end homework, so that was very helpful. I have my end value from my command line argument, and I just add up all the same values here, or all the same counts, I guess, or all the counts associated with the word, and then put those in the tree map, and then just constantly prune the smallest one every time I add a new one to the tree map, as long as I'm at the size. And so that I'll always keep it. I have 10 here. That was just the boilerplate comments from my homework. But yeah, basically, as long as its size, if its size increases by past the top end value, it'll just always limit it to that. And then cleanup is just, it writes everything, or it writes the word and the count as to context, and it does that the amount of times that we have top end. So that's why I always get the correct number of results. And the driver, again, pretty standard. I have my command line argument here. I actually do use a combiner here because I'm able to I have the text in long writable as both the input and the output type, so I have it in such a way that it can be combined kind of in the middle between the mapper and reducer, so it helps take off some of the work there, hopefully make things a bit faster. Reducer class, output key, output value is text, long writable. And if I don't give it, if I don't make it one reduce task, this is something I actually discovered in the homework. But if I don't set this specifically, it will use multiple reducers, and I will get multiple sets or multiple times the amount of answers as the number I give it for top end. So if I give it 5 for top end, it will actually give me multiples of 5, I think, or 5 times the number of reducers because of that. So I had to make sure I set this to 1. And that's why I have the combiners here, is to take the load off the reducer, so the reducer isn't doing everything. I can have many combiners as long as I just have one reducer at the end to kind of put everything together. All right, last set of files here. word search. This one was probably the most, probably the easiest of the three, I think. Get the word from the command line argument, very simple. I've done this in the other two. When I map, I just break out the word and the rest of its file information. And again, I just, as long as it's the word I'm looking for, I write the new word, and I write the rest of the information that comes with it, because I do want to know the file, the folder, and the count with it. Unlike top and row, I only want to know the count, basically. So just write that. So this will sort out most of the words because I'm only really looking for one word in particular. So that's pretty straightforward. Word search reducer. Here, again, super simple. Basically, for each value, I just write the key and the value. So the key again is the word here, and the value again is the folder file name structure with the count, and I don't need to worry about parsing any of that, doing anything fancy, because as long as I have those individual that are kind of written out to context, then I can just break those apart when I get back to the GUI and to the individual kind of rows of the table. So it makes things very, very straightforward. And lastly, the word search driver. Again, very standard. I have my word command line argument. I don't want to use combiner here or anything. Just have mapper reducer. Both output key and value at text. I also did set the one reduced task just to be sure that it wasn't giving me multiple results, even though I am very searching only for a particular word. I just wanted to be sure. And since it wasn't really much of an intensive reduce task, because I'm only looking for one thing in particular, it's as you saw, it's mostly fine. It doesn't take too long to run. So yeah, that's about it for my project. I am going on 43 minutes here, so I will cut myself off now so I don't bore you to death. Thank you for the chance to do this project, and I'll definitely recommend this to all my friends. Thank you very much.